All right. Next, we'll have our keynote speaker. It's my pleasure to have Dr. Edward Knightley, who will talk about new spectrum access capabilities about 100 gigahertz. He is the Schaeffer-Lindsay Professor of Electrical and Computer Engineering and Computer Science at Rice University. He received his PhD and master's from the University of California at Berkeley. He is an ACM Fellow, an IEEE Fellow, and a Sloan Fellow. He received the IEEE Infocom Achievement Award, the Dynamic Spectrum Alliance Award for research on new opportunities for dynamic spectrum access, the George R. Brown School of Engineering Teaching and Research Excellence Award, and the National Science Foundation Career Award. He won 8 Best Paper Awards, including ACM Mobicom, ACM Mobihawk, IEEE Communications and Network Security, and IEEE Infocom. He serves as an editor-at-large for IEEE ACM Transactions and Networking, and serves on the Scientific Council of India Networks in Madrid and the Scientific Advisory Board of INESC at EC in Porto. He served as the Rice EC Department Chair from 2014 to 2019. Edward?
Thanks so much, John, for that introduction and also for the invitation. It's an honor to be speaking in front of all of my distinguished colleagues and friends, and I'm looking forward to being able to share with you some of my thoughts on spectrum above 100 gigahertz. So let me Okay. Well, when John invited me to give the talk, the first thing I did, of course, is to ask ChatGPT what I should say. And it gave me a really nice title, Navigating the Spectrum, Charting the Future of Connectivity. Isn't that a wonderful title? I didn't use it, though, so any of you, if you want it, you can have it. And the outline is actually very nice, too. I really encourage everyone to ask ChatGPT for a talk, because then it kind of gives you the aggregate of every other talk that's been given.
There's a repetition, though, in the bottom.
That's right. So their ChatGPT, as we know, can stumble on itself. So I'm not going to talk about any of this. Sorry. I'm going to talk about what are some of the new things, what's new, and what are the challenges and what's enabled by the new spectrum. And I want to just warm up with a couple things that probably everybody in this room knows, but I think it bears repeating about why are we excited about new spectrum above 100 gigahertz, millimeter wave up to sub-terahertz. And we'll start with the wider bandwidth, that the 20 megahertz channel that we're using in this room, I didn't check to see if we're channel bonding, but we might be up to even 160 megahertz. But then we compare that to 2 gigahertz channels in 60 gigahertz, and maybe even beyond, maybe to a 20 gigahertz channel. And who cares about it? Well, the W out front for Shannon's capacity is that bandwidth. So as we go from that little blue sliver to the big red wide one, then we can be expecting our data rates to go up as well. The other thing that you all probably know is the sensing resolution story. That whatever type of sensing we're doing, whether it's radar or trying to do some imaging, that we've always got a wavelength limitation for our resolution. And so if we can get down to millimeter scale wavelength, then we can get down to a millimeter scale sensing resolution. And so again, whether we're doing imaging or whatever we want to know about the environment that's around us, that reduction in wavelength will help. Now let me get to a couple things that maybe you haven't thought about being above 100 gigahertz. And one is that there's new relevant models. And so I spent most of my wireless career working in frequencies below 5 gigahertz. And in those cases, the near field is less than a meter typically. And so it's this little bubble around the access point that you really never think about. You really don't develop models or figure out, oh, what's happening if I'm just right up there against it? It's usually up in the ceiling, right? So you can't even get within a meter of it. So we ignore the near field. But now the near field is 2 times the diameter of the aperture squared divided by the wavelength. So the access points aren't shrinking. We're not going to give a tiny millimeter size access point, or the phone. The phone's going to be the same size, the access point's the same size, so the numerator is fixed. And now we've just changed the denominator by a couple orders of magnitude lower. So now we can have near fields that are tens of meters, right? And so, well, who cares whether in the near field or far field? What does it matter? It's just an equation, and can't we communicate in either? And yes, we can communicate in either. But the wonderful thing is that we can do very different things in the near field that we can't do in the far field. And I'm going to give you an example of it in the talk. The simplest one is focus. So if we think about beamforming, then I might say, well, I've got a beam and I'm going to put it over in this direction, this sector right here, and I'll spread it out all over this area, right? And we don't think of focus. We don't think of, oh, I'm going to put a spot on a particular chair, for example. You just don't think about that way in wireless, but now we can focus. And this is not the reactive near field, by the way. So if you touch your smart card to something, and that's a reactive near field. And so this is the communication near field. Some new devices that we just haven't thought about previously, and one that I worked on for a few years is a leaky wave antenna. And this antenna, I wrote new in parentheses relevant because it's been around since the 1950s, but it has this property of angular dispersion, that the angle that the radio waves emit is a function of the frequency. And so if you think about it, if I start switching channels, then I start steering the beam just by switching the channel. And that's a wonderful property if you're trying to do beam steering at very high frequencies, because then I can tune the frequency in order to beam steer with no antenna array. This is one antenna. And I show it with parallel plates because you can actually build that in your lab and machine shop and just put a little slit in it. That's why it's called leaky, because it leaks out the side. But there's CMOS versions of this as well for implementation. But so these are a radically different way of thinking about antennas. We don't think about MIMO, don't think about phased arrays, but a single antenna with a very unique property. New relevant abstractions, the electromagnetic wave. So when we wireless people think about what's the abstraction that we have with a wireless channel, probably if you go way back, maybe you just thought about it as at a packet level abstraction. And lots of people at higher layers just do think about it that way. In other words, the wireless network is something where you put in a packet and just randomly or for whatever reasons it just gets lost sometimes. Could be a collision, could be a bad channel, packet received or not. That's all the abstraction you need. The abstraction that most of us used, and I used for a lot of my research, was a symbol level abstraction, and that you send in these symbols X to the network, and they get transformed by a linear matrix H, and they get noisy. And so that H has been amazing for sensing as well, right? You want to count the number of people behind the wall? Well, that's an H problem. Throw some machine learning at that H, and you'll figure out how many people are behind me, right? And so it's been a very valuable abstraction at lower frequencies. But as we get to higher frequencies, new abstractions are needed. So the channels are starting to look almost optical, quasi-optical channels. There's very wide bandwidth and frequency-dependent responses. We're not talking about is the channel flat or not flat, but things like a leaky wave antenna, that the directivity could be completely different at different frequencies. New sensing opportunities beyond H. So we're writing sensing papers, and there's no H in it at all. So we have new devices, and we can just be thinking about the abstractions in different ways, down to the electromagnetic wave. New small form factor metasurfaces. So devices that we can put on a phone, that they can be on an access point. Metasurfaces are exciting to me because now we can shape the incoming and outgoing waves at an unprecedented scale. And I'm going to give you an example of, well, again, what's the big deal, right? Let's make sure we can do something useful with this other than just, wow, this is really cool. But so we can rapid prototype them in the lab, print them. I'll show you a little bit about that later. And also, of course, in CMOS. So if you start to put these kind of new building blocks together, then you can get to new capabilities as well. And so what's an example of a new capability? One of the papers, this is Yasemin Ghasempour's thesis work, and was one-shot localization. And so the idea is if you have a leaky wave antenna that transmits different frequencies in different directions, well, if we excite that with a high frequency, so shown here with a light analogy, so put in white light, what's it going to do? It's going to separate it in frequency. Wonderful. Then you all know instantly where you are relative to me. Because if you're seeing red, you're over here. If you're seeing violet, you're over there. And so you just all localize yourself with respect to me within a nanosecond, right? So again, there's no there's no antenna array. It's a single antenna, and it's a very fast, way of doing localization. Other things, I just talked about the near field and how excited I am about that. And that often makes people think, well, these links are just really short. We're only going to be going a meter or something because of that word near. And so it's really amazing how backhaul is also making big advances. And so there's some commercial advances, Nokia and Ericsson, at one at 150 gigahertz and another at 100 gigahertz. And these are kilometer scale. So the one in Greece was 1.5 kilometers. And Josep Jornet built a link, at 2 kilometer link at over 200 gigahertz. And so these are data carrying backhaul, wireless backhaul links, so they can go long distance. Okay, so what I'd like to do with the remainder of my time is give 2 examples of some projects in my own work about exploiting these new capabilities in 2 different directions. One is in security, and the other is in beamforming. So I'll talk about both those. So the first one, securing a highly directional link. So Josep puts up a link. It's at sub-terahertz. He puts it between 2 buildings, Alice Inc., Bob Inc., and it would seem that no one can possibly intercept this link and eavesdrop on the link. So the threat that we worked on in collaboration with Josep is a metasurface in the middle attack. In other words, an aerial metasurface is going to fly between Alice and Bob, intercept the link, while letting Alice and Bob communicate so that they don't know that the link is being intercepted. So a literal over-the-air interception. And how does Eve know where to put the metasurface? Well, all of the backhaul links, wireless backhaul, are on a public database, FCC, so you can easily find them. Okay, so some research question. How does Eve design a metasurface so that it's transmissive between Alice and Bob, and so the signal goes right through, yet creates a diffraction link for Eve? How can we do that? And so we'll put it on a transmissive substrate so it can go through, and we'll have little metallic meta-atoms on it that will create a diffraction link in the direction that Eve is going to be. We'll fabricate it for whatever carrier frequency that Alice and Bob are using, and we'll do an experimental validation, i.e. we will truly fly a drone into the space between the transmitter and receiver. So how does one do that? So this is where, again, we get to different abstractions of the channel, right? We're not going to start with, okay, we've got massa MIMO and H, and let's try to figure out what the channel should do. We're going to start with Snell's law, right? And you normally don't start a wireless project with Snell's law. So this is generalized Snell's law. So we're not going to go from air to water and two mediums that you saw in high school, but if you have a discontinuity at the surface, so at the interface, if there's a phase discontinuity, then you create a diffracted link at a different direction. And so can we create a phase discontinuity? Yes, we can with a metasurface. So rather than let the, well, what we'll do is we'll have Alice send straight through to Bob, and then we'll create a copolarized separate link off here to Eve. And that phase, so if you remove this yellow part, that's the Snell's law you remember. And so C speed of light and FC's our carrier frequency. And so this is a phase gradient that we're going to put on the metasurface to create the second link. How do you put a phase gradient on a metasurface? What does that mean, right? If you're an antenna person, then you think about a phased array I can steer by putting a phase gradient on the antennas. That the first one has 0 degrees, the next one is 10-degree delay, 20-degree delay, 30 degrees. So that's what I mean by phase gradient. Okay, so how will we do this? We will take meta-atoms. So these are small pieces of metal. It's a radiating element, so it's going to absorb and re-radiate electromagnetic energy. They're sub-wavelength size, so we'll be putting maybe 4 or 5 of these per wavelength. And the one I'm showing here is called a split ring resonator. And so it's got a ring with different opening size. We can electronically control the opening size, or we'll do static metasurfaces in this project, so it'll be fixed. And we'll go atom by atom with these meta-atoms to create that phase profile that I said we needed according to generalized Snell's law. So the phi dx, we just want to be a constant because we want a constant angle where Eve is going to be. So how do you do that? Well, so we'll put d phi dx is to be some constant, 2 pi over gamma, and that'll be our spatial period. So 8 meta-atoms, all the numbers come out. Remember, we've got a speed of light in there and so on in the main equation, but it'll be about 6 millimeters across the atoms. So if you look across the metasurface, you'll see a pattern that looks like this. I'll show you the printout of one in the next one. But if you really zoom in, you'll see these repeated down in columns, and then the meta-atoms are shaped like this. And so the red is the phase gradient that we want to steer wherever Eve is going to be. So we pre-design, Eve says, I'm going to be 22 degrees away from Bob, so that's where I'll be, so I want this gradient. Okay, so we printed them. So you can do CMOS programmable, but in this case, we didn't need a programmable one, we just needed a static one. And so we printed one. And the way, the trick to printing these, if you're working at a millimeter wave and above, they are extremely easy to do in your lab, and I really encourage you to do it. It may be $200–300. NSF won't even notice that on your budget, right? We're just gonna print these. And so how do you do it? You buy a laser printer, you print a pattern of the C-shapes in a normal laser printer. So you just have, there it is in paper. Well, now how do we get it to be metal? Well, take a metal foil that you can buy at an art supply store, and then heat and pressure bond the metallic powder to the toner. So this is also the laminator is a standard office laminator. So you can make these, and then they can allow you to manipulate the electromagnetic waves in any way that you want. And how big it is just depends on the wavelengths. So if you have a normal office printer, you can go down to, in this particular example, we're at about 150 gigahertz. If you want to go higher frequency than that, then you need a better printer. Okay, so we did a validation at the atrium, and this is an atrium at Northeastern University with Josep and his team. And so we started with Alice over here, and then there's the metasurface in the middle, and then there's Bob receiving, and then Eve goes off to the side. And with this, we did a lot of tests to see, is this thing even going to work? Because the drone, in the end, is going to be vibrating. And we thought, we just printed this sub-wavelength millimeter scale thing, and now we're going to shake it around. That just doesn't seem like a good thing for wireless. So this was one of those experiments where you really don't know if it's going to work, right? So we thought before we go outside and fly it around, let's just put it on a vibrating plate, shake it a little bit, and see if we can still close the link. And the answer was, yes, we could close the link. So all the indoor experiments were positive. And so then we took it outdoors. But so there's two parts. So one is, does Eve get it? And so if you don't have a metasurface and Alice is just trying to eavesdrop, she's not going to get anything because this Alice Bob link is so directional. So this is a super directional link of maybe a few degrees beam width. So the pencil-like beam. So Eve's not going to get anything. With MetaFly, so the drone flies in there with the metasurface, now it creates a diffraction link at Eve's predefined angle of 22 degrees. Remember, she had to set up the phase gradient according to where she was going to be. So this could, again, it be dynamic with something programmable, but in our case, we did a fixed printed metasurface. So Eve gets the game. So Eve's able to eavesdrop on the link. But can Bob detect it, right? We put this thing, this metallic transmissive metasurface, it's a bunch of little pieces of metal on paper. You saw the picture of it. Can Bob figure this out? So without the metasurface, that's Alice and Bob's response. And then with it, they only lose about a few dB. So, how did this work? How can Eve get all the gain? Bob didn't lose anything. It feels like, are we doing, is there a trick going on here? And well, the meta atoms really are doing a little trick. They're absorbing some of the energy, re-resonating it at a diffracted angle, at a different polarization, and adding some gain to it, beamforming gain, because it's not just scattering it any direction, it's scattering it at a specific direction of 22 degrees away. But straight through it, it only cost a few dB. So is a few dB a big deal to Bob? Maybe, maybe not, because you can get variations like that from swaying buildings, weather, and so on. So maybe Eve won't notice, or Bob won't notice. Depends how sensitive Bob is. And the rooftop validation, the grand finale of all this was, let's see, this is my student, Alice. And then there's Bob across there. Joseph is probably somewhere in this picture. Are you in that picture? They forced a professor to be there the entire time for security. And so lucky for me, this happened not at my university. So Joseph got to be the one to be there. So we've got across across the street, two buildings, and then the drone is holding the printed metasurface, and it flies between them. And so we demonstrated it. It won a Best Demo Award, and it's going to be at IEEE SMP, I think in a week or so, the metasurface in the middle. So some broader open challenges for security. Well, we have new devices and wide bandwidth, metasurfaces, new electromagnetic capabilities. And the question always asked is, as we get excited about these new devices, what's going to happen when the adversary has one of those, right? You have to always ask that question. What can the bad guy do with these? And so a printed metasurface, we literally make these in 2 minutes, attached to an off-the-shelf commercial drone can now intercept a rooftop link. So the security challenges to me are envisioning adversaries that can manipulate electromagnetic waves arbitrarily. And that's a extremely powerful adversary that we'll have to think about for countermeasures. Okay, and the second challenge that I wanted to talk about for high directivity, or for being above 100 gigahertz, is high directivity. So if you remember that first slide, and I said, well, isn't this W we get from Shannon wonderful? We're going to go wide bandwidth, right, and get linear increase in the data rate. And the fine print was, well, if the SNR stays the same, the signal-to-noise ratio, right? So how do we keep the signal-to-noise ratio the same while we're getting these path loss reduction that increases with frequency? And the answer is beamforming. I think probably most people in this room know that. So when we're in millimeter wave to sub-terahertz, we are using beamforming to overcome the path loss. So we can think about these directive beams, maybe 3 degrees wide, 10 degrees, something like that should be in your mind. And now the downside of having very narrow beams is, what about a blockage? What happens when someone walks between you and the beam, or even you block it yourself, right? Access points are usually up high, and so if I turn around and look at my phone, then I've actually just blocked my own link, right? So if it's not going to be resilient to blockage, then we're going to have outages, which will be obviously not desirable. So the usual way to overcome this is to use a reflected path. And so if the access point's up there, well, maybe this wall will give me a nice reflected path, and I can use that reflected path to reach my phone if I'm blocking in that scenario. That would work. You would get a very nice specular reflection off the wall. Or there's a lot of work in intelligent reflecting surfaces. And so maybe this is only going to give me a specular reflection, but maybe I don't want specular. Maybe I want it to come in at 45 degrees and go out at 30 degrees. Right? So an intelligent reflecting surface can give me those angles that I want. So the question is, what if I'm not lucky and I don't happen to have a nice flat surface behind me? What if this was too rough or it's not behind me? And there's no reflect IRS either. There's no intelligent surface. I just don't have the surface and I'm blocked. What does it mean? Game over, go back to lower frequencies, get all those reductions in data rate. So what I'll try to spend the rest of my time convincing you is that we can curve the beam. So we'll curve the beam around the obstacle. Now, as soon as I suggest that, you're probably remembering back to physics days and when you saw Maxwell's equations and light emerged out of these equations. You say, wow, if we have all these equations, they're all satisfied, then light can propagate, electromagnetic waves can propagate. And so all the waves that you saw in those classes were straight. They were plane waves, or maybe they're spherical waves emitting out in spheres, but they didn't curve. So we have to ask the question, does Maxwell object to this? And so there's a beam called an Airy beam that has a quadratic path. And the story with Airy beams is theoretical physicists in 1979 showed that they exist. They are a solution to Maxwell's equations. Normally you solve and you get plane waves and build things out of that, but there's also a quadratic solution that the theoretical physicists showed. And they satisfy the wave equation. So they propagate, they satisfy Maxwell's equations, and everything, the math of waves holds. Now the question is, how do you generate one? So about 10 years later, some experimental physicists generated one with light. And with light, they had a monochromatic light source, a laser, and curved it. So we're not the first to ever curve light. What we're the first to do is send data on it. So what's the big deal of sending data on it? Well, then you have to modulate it. You have to have bandwidth. You have to have it in a communication system, not just a monochromatic laser. So how can we curve data? That's the question I want to address. So there's so the function I'm showing right here is called the Airy function, and it looks crazy. It should look crazy. You've got the amplitude is in blue, and it's oscillating on the left side and then flattening out on the right side. And the phase is shown in red, and it's just going positive and negative, so 0 and pi. And the function AI is the Airy function, and x naught is a parameter that controls the curvature. And so what does this function mean? That's the x-axis is the physical dimension of the metasurface, or the aperture, the transmitting aperture. So what the theory tells you is, if I take this function and I transmit an electromagnetic wave, launch it with this characteristic, then it will curve. That's what the theory says. And so here I'm showing z, so it's propagating up this way. We're showing small dimensions, but we'll get up to meter scales and so on later. but just to zoom in and just show you, this is what it would look like. So this is a heat map of the wave curving in space. So if the wave just goes straight, then the red would just go up straight. So let me give you a little context, because actually you already have some context to interpret this. And that is beam steering. Remember with Eve, earlier in the talk, Eve just wanted to create a diffraction link, beam steer, right? So how do you beam steer? Well, you set an amplitude function to 1. You don't want to attenuate it. Well, we had meta-atoms, so instead of 1, it was down here at 0.3. We did attenuate. But ideally, you wouldn't attenuate at all. And if you want to beam steer, then you put a phase gradient on it, right? Don't just make the phase flat, but put a phase gradient over space. So that's what we did in the first part of the talk. That's what it looked like. And now, if we want to curve the beam, we have to put this function on it. And this is, again, another one of those experiments where we think, is this possibly going to work? It took us a couple of years before we got anything resembling a curve. There were some of the initial ones, if you kind of really squint, you might say, yeah, it looks like it's curving a little bit. But eventually I'll show you something that hopefully you'll be convinced is truly curving. Okay, so this is the function we have to put on the metasurface. That's the message. So how do you put that function on a metasurface? Well, you think of the meta-atoms as just sampling this function. A meta-atom gives you an amplitude and phase, and so I would just want to approximate that curve the best that I can. So I'll choose my meta-atoms according to the value that I want in the function. So here I've got an atom that's C-shaped, kind of oriented with the gap perfectly horizontal. That actually attenuates the maximum energy going through it. So if I put those, then I get an amplitude near 0. And then I want maximum amplitude, so I rotate those about 45 degrees. And so then I'm going to tile them along the metasurface. So same thing as before. My metasurface is going to look like a tiled thing. Rather than Eve diffracting it, now we have a metasurface that's going to curve the beam. Okay, so here's the experiment, the heat map, and this is a tabletop experiment that we always start our experiments tabletop because we've got extremely high resolution analysis using time domain spectroscopy. So it's really valuable equipment once you get above 100 gigahertz to get everything understood on the tabletop level before we go out to do larger distances. And why is it tabletop? Well, it's sub-microwatts. So if your transmit power is sub-microwatt, versus tens or hundreds of milliwatts, which you would normally use on a phone or an access point, orders of magnitude less over an entire terahertz. So the spectral power spectral density is extremely low. So it doesn't go very far, but we can still see, is it curving? And so here's the heat map at 150 gigahertz, and you can see that the theoretical trajectory shown here in black, and then we were able to still get curvature, and we fit it. Does it really fit a parabola better than a line? And yes, it does significantly, so I won't show you all the data there. But what I want to show you instead is an example of a blockage. And so this is, I'm going to play a little video of a scenario here. And before I play it, I'll just set it up to say, what's going to happen here. So we've got a transmitter in the foreground, and then in the background, we've got a receiver. And this black thing here is a wall that we're going to push in front of the line of sight path between the transmitter and the receiver. So we're going to block it. So we're going to curve the beam around the blockage. But I also said we would be the first to do it while sending data. And so to send data, we're going to modulate. It's going to be on-off keying. So here you'll see an old school eye diagram. And if the eye diagram is open, then you'll say, wonderful, data going through. If it closes, then we have errors in a higher bit rate. And what I'll do too is show you a few different cases. One is you don't steer the beam. So if you don't steer the beam at all, then as we saw with the eavesdropping, the receiver gets nothing. Then we'll steer the beam using traditional beam steering. So we'll just put a phase gradient on it, go straight to the receiver. But then that's going to start to get blocked. So then to get around the curve, or to get around the obstacle, we'll curve it, and you'll see one of the postdocs come into the video to change, we'll have a metasurface. Actually, here we'll use a faceplate, but you'll see it switched between one that just steers the beam versus one that curves the beam. Okay, so so there's the eye diagram. It's closed, and now now it's beam steering. So it's beam steering. It's not blocked. Open eye diagram. Everything's going well. But now you'll see the wall closing in, and now it's covering the line of sight path, and you'll see the eye diagram closing. And so now there's a high bit error rate. And so we're blocked. The bit error rate is high. And so instead of steering the beam, let's curve the beam. And so now the beam is set to a quadratic path, and you see the eye diagram opened up again. So the bit error rate is reduced, and the link is closed again. And so we'll move the obstacle now out of the way, and you can see that it's still communicating with or without the obstacle, the curved beams. So the beam steered one got blocked and got high error rate, and the curved one got around. So just to give you some numbers on it, and maybe to just quick refresh, that without any beam steering, the beam's just going in the wrong direction, and the bit error rate's 0.5. Steer the beam in the normal way with a phase gradient, and then now the beam's going in the correct direction. The eye diagram opened up, the bit error rate was 10 to the minus 7. Now the wall came in with the steered beam, and the bit error rate went to 2 times 10 to the minus 3, and then curved the beam, and the bit error rate improved by about 3 orders of magnitude. So we can't get back to perfect as if the obstacle wasn't there, which was 10 to the minus 7 bit error rate, but we got it from 10 to the minus 3 down to 10 to the minus 6. So the curving the beam did better than beam steering. Okay, so some open challenges. Well, we've got to figure out where to curve this beam, right? Because first of all, it's blocked, right? And so if it's blocked, how do you know where to even go, right? So in an analogy, we're trying to kick the soccer ball. The analogy is great too, because you don't, I don't play soccer, so I have no idea how this works. Maybe somebody can explain it to me during lunch. But the ball curves with nothing, no interference after the kick, right? And it's the same with that aperture. You set it off in the right direction. There's no tricks being played once the beam launches. It's going to curve, right? So it's all about the launch, but you have to know where the path is that you want. And we've got new parameters here, right? We think of beam steering as, well, maybe it's an angle or H, right? A lot of you probably think beam steering is H. You know, give me H and I'll tell you the weights, right? And so here we can think of it as, well, there's a location and we're trying to curve around something. So we're basically trying to put parabolas onto, in space to find the receiver. When to curve versus direct beam forming, and also there's great challenges in sensing, right? Because if we could curve a radar signature, we could curve anything that you want to curve. Data plane. Now we have wide bandwidth, so the curvature is a function of frequency. So all the parabolas that we're getting have a lambda in there in terms of their parameterization. And so now you can think of the soccer ball. The wider I go, you're basically kicking a family of balls, all that have a little bit different curvature, right? But you want them to all land on the same spot, right? So this is what I mean about frequency dependence is huge now. We can't just ignore it and say, well, I did it at 150 gigahertz, so who cares if I go plus or minus 20 gigahertz. So it really does make a big difference, the wide bandwidth. Okay, and to close just with some other big challenges above 100 gigahertz, some things that I think are really interesting. First, the low-cost, energy-efficient components. So we're collaborating with circuit designers to get all of this in CMOS. Sensing and learning with the wave model and Maxwell's equations as a baseline versus the black box. So for example, the counting people behind the room with H, right? That doesn't make any sense at all to try to bring physics into that problem. It's just about H and training and learning. So a black box model absolutely makes sense. But now if I want to sense the room doing curves, actually I know the quadratic path. I know a lot about where that beam is and where it's potentially landing, and the reflections coming back tell me a lot as well. But that might just tell me, well, there's a piece of metal somewhere, or there's a reflection, or there's a rough surface. But I still want to learn beyond that, right? That's not what we want to know in the end. We want to know, are there people, health maybe, are they healthy, and try to understand more about our environment. So rather than just pure black box learning based on raw signals, we can say, no, we actually have an excellent physical characterization of the entire system, the transmission and reflections coming back. Diverse spectrum to fuse spectrum. So the low frequencies will never go away. We always need to remember that we keep putting more and more radios on the phones, putting more and more radios on the access points and the infrastructure, and so all of those will be working together. And so there will be a time and a need for the different frequencies, and they can potentially aid each other as well. Network optimization and management to harness all these new features. So a lot of times I'll call these control plane problems for short. And so as we bring in more and more capabilities, then the operator of the network has to figure out when and where to use them. The area beam curving was a great example of that, right? That it's not going to be part of the standard of you must curve this way or you must curve that way, but it's going to be a capability in future access points or future phones. And so someone is going to have to put a control plane on them in order to optimize it. And lastly, as I mentioned previously, the new security threats and capabilities. So to summarize, we've got very new building blocks. So the devices are new, the leaky wave antennas, the meta surfaces, being in the near field, thinking about waves versus just thinking about the linear matrix H, and starting to think about wireless in a new way, about wavefronts. And this will give us new architectures and new capabilities, flying meta surfaces and curving beams. So if you're interested in some of the papers that I talked about, they're all on my group webpage, and I acknowledge all my students who did the hard work building the meta surfaces and running the experiments, and the collaborators. I mentioned Josep, also Muriel, Dan, and Kaushik. Dan is a physicist at Brown University. Muriel, I think everyone here knows, and Kaushik is a circuits designer who builds CMOS meta surfaces in addition to other things. And of course, thank NSF for feeding these very hungry grad students and making it all possible. So I'll stop there and thank you all very much.